Welcome to this model. And this model, let us have an insight of attenuators and power dividers. Attenuator is a device used to control the amount of microwave power transferred from one point to another point on a microwave transmission. So it is a passive two-port device used to control the power levels in the microwave system by partially absorbing the transmitted signals. Attenuators can be classified as fixed and variable attenuators. Resistive films like aquadrag are used in the design of both fixed and variable attenuators. Attenuators control the power flow in this direction. Fixed attenuators provides only a fixed amount of attenuation. It consists of a dissipative element called pad. Pad is placed in a waveguide. The pad is placed in such a way that the plane is parallel to the electric field. For this, two thin metal rods are used. The pad is tapered, which provides a gradual transition from the waveguide medium to absorbing medium of pad. It also reduces reflection. The amount of power that a fixed attenuator can absorb depends on strength of magnetic and dielectric field, location of pad within the waveguide, and the frequency of operation and area of pad and pad material used for power observation. So this diagram shows the fixed attenuator. Here the thin metal rod and power absorbing pad are placed inside the waveguide which absorbs the microwave power. And now let us see about the variable attenuators. It provides a continuous attenuation. The amount of attenuation is controlled by depth of insertion of the absorbing plate inside the waveguide. For this, a knob and gear assembly is used. A knob can be calibrated suitably, and the maximum attenuation will be offered when the pad extends all the way across the guide. So types of variable attenuators are rotary attenuators, electronically controlled pin diode, and FET attenuators. This diagram shows the variable attenuator. So by adjusting the knob, we can control the position of the resistive cord inside the waveguide. So flap is mounted on the hinged arm and allowing it to descend into the center of the waveguide. Degree of attenuation can be determined by the depth of insertion. And now let us see about the resonators. In general, a cavity resonator is a metallic enclosure that confines the electromagnetic energy. The stored electric and magnetic energies inside the cavity determine its equivalent inductance and capacitance. The energy dissipated by the finite conductivity of the cavity walls determines its equivalent resistance. In practice, the rectangular cavity resonator, circular cavity resonator, and re-entrant cavity resonators are commonly used in microwave applications. Theoretically, a given resonator has a finite number of resonant modes and each mode corresponds to a definite resonant frequency. The mode having the lowest resonant frequency is known as the dominant mode. Here is the sample of a rectangular cavity. So microwave cavity acts similar to a resonant circuit with extremely low loss at a frequency of operation, resulting in quality factors up to the order of 10 power 6 compared to 10 power 2 for the circuits made with separate inductors and capacitors at the same frequency. So the wave equations in the rectangular resonator should satisfy the boundary conditions of the zero tangential E at 4 of the volts. And these functions can be found as such as equal to Hn into cos of m by x by A into cos of n by y by B into sine of P by Z by D. And m is equal to 0, 1, 2, 3 and so on represents the number of the half-wave periodicity in the x direction, and n represents the number of half-wave periodicity in y direction, and p represents the number of half-wave periodicity in this direction. So Ez is written as E of P is into sine of m by x by A into sine of n by x by y B into cos of P by Z by D. Okay. So the separation equation for both TE and TM modes is given by k squared is equal to m pi by A the whole square plus n pi by B the whole square plus p pi by D the whole square. And the resonant frequency is expressed as Fr, and it is given by the equation that is shown in the slide. So here is the method of excitation for rectangular resonance. The maximum amplitude of the standing wave occurs when the frequency of the impulse signal is equal to the resonant frequency. So a circular cavity resonator is a circular waveguide with two ends enclosed by a metal wall. The field solutions of a cylindrical cavity of length L and or radius R follow from the solutions of the cylindrical waveguide with additional electric boundary conditions at the position of the enclosing plates. So the wave functions in the circular resonator should satisfy the Maxwell's equation subject to the same boundary condition described for a rectangular cavity resonator. The separate equations for T and Tm modes are given by k squared is equal to x and p by the whole squared and q pi by d the whole squared for T mode, and k squared will be equal to x and p by a the whole square plus q pi by d the whole square in Tm mode. And the resonant frequency is given by 1 by 2 pi square root of mu epsilon into square root of x dash and p divided by a the whole square plus q pi by b the whole square. And here is the equivalent circuit of the resonator. It can be represented as that of a simple LC circuit. A microwave cavity, the stored electric energy is equal to the stored magnetic energy at resonance, as in the case of resonant LC circuit. Now let us see about the Q factor of the cavity resonator. The quality factor is a measure of the frequency selectivity of a resonant or anti-resonant circuit, and is defined as Q is equal to 2 pi into maximum energy stored by energy dissipated per circuit, that is W omega by pi. So at resonant frequency, the electric and magnetic energies are equal and in time quadrature. The total energy stored in the resonator is obtained by integrating the energy density over the volume of the resonator. So W is equal to integral epsilon by 2 modulus of E squared into dP. Okay. Where E and H are the peak values of the field intensities. The loaded QE of the system is given by QE is equal to omega naught into L divided by R plus N squared into Z. And the coupling coefficient of the system is defined as K into N squared in K is equal to N squared into ZZ by R. And the loaded Q would become QR is equal to Q naught by 1 plus K. That is Q, the 1 by Q is equal to 1 by Q in plus 1 by Q extra. And there are three types of coupling coefficients called critical coupling. If the resonator is matched to the generator, then K is equal to 1. The loaded QR is then given by QL is equal to 1 by 2 into Q extra is equal to 1 by 2 into Q naught. And the second case is overcoupling. If K is equal to 1, the cavity terminals are at low voltage maximum in the input line at resonance. The normalized impedance of the voltage maximum is the standing wave ratio, that is K is equal to P. Undercoupling occurs if K is equal to 1. If the cavity terminals are at a voltage minimum and the input terminal impedance is equal to the reciprocal of the standing wave ratio, that is K is equal to 1 by rho. So here is the diagram which shows the relationship of the coupling coefficient and the standing wave ratio, which shows the undercoupled and overcoupled regions. Now let us discuss about the power dividers. The power divider is a passive network component that is used for power division and power combining. It is a lossless network. It divides the input power into a number of smaller amount of power. It can provide either equal or unequal division. Simplest power divider is a T-junction. It is a 3-port network. 4-port network is a directional coupler and hybrids. So this diagram shows the power divider and power coupler, which divider will divides the power, whereas the coupler combines the power. And the types of power dividers are T-junction power divider, resistor divider, Wilkinson power divider. The T-junction power divider is a simple 3-port network that can be used for power division or power combining, and it can be implemented in virtually any type of transmission line medium. And here this diagram shows some commonly used T-junctions in wavegates and microstrip line or strip line form. The junctions shown here are in the absence of the transmission line loss, lossless junctions. The lossless T-junction dividers can all be modeled as a junction of 3 transmission lines as shown in this figure. Here, the higher order modes associated with the discontinuity of such a junction leading to stored energy that can be accounted by a lumped susceptance B. In order for the divider to be matched to the input line of the characteristic impedance Z0, we must have Yn is equal to JB plus 1 by Z1 plus 1 by Z2, that is equal to 1 by Z0. If the transmission lines are assumed to be lossless, then if you also assume B is equal to 0, then the characteristics impedance reduces to 1 by Z1 plus 1 by Z2 is equal to 1 by Z0. In practice, if B is not negligible, some type of discontinuity compensation or a reactive tuning element can usually be used to cancel the susceptance, at least over a narrow frequency range. So the output line impedance Z1 and Z2 can be selected to provide various power division ratios. If necessary, quarter wave transformers can be used to bring the output line impedance back to desired levels. So if the output lines are matched, then the input lines will be matched. There will be no isolation between the two output ports. However, there will be a mismatch looking into the output port. And the second category is a resistive divider. If the 3-port divider contains lossy components, it can be made to be matched at all ports, although the 2 ports may not be isolated. So the circuit for such a divider shown in this figure, that is resistive divider. An equal split divider is shown, but unequal power division ratios are also possible. So the resistive divider can be easily analyzed using circuit theory, but assuming that all ports are terminated and the characteristics impedance Z0, the impedance Z seen leaking into the Z0 by 3 resistor followed by a terminated output line is given by Z is equal to Z0 by 3 plus Z0, that is 4 Z0 by 3. Then the input impedance of the divider Zin is equal to Z0 by 3 plus 2 Z0 by 3, that is equal to Z0. Okay. And which shows the input is matched to the feed line. Because the network is symmetric from all 3 ports, the output ports are also matched. That is, when S11 is equal to S22 is equal to S33, that will be equal to 0. If the voltage at port 1 is V1, then the voltage division, the voltage V at the center of the junction is given by V is equal to 2 by 3 into V1. That is, V1 into 2 is Z0 by 3 divided by Z0 3 plus 2 is Z0 by 3. By cancelling out the equations, we will get this as 2 by 3 into V1. And the output voltages are again by voltage division, we can find it by V2 is equal to V3, that is equal to V into Z0 divided by Z0 plus Z0 by 3, that is equal to 3 by 4 V, that is equal to 1 by 2 into V1. And the network is reciprocal, so that the scattering matrix is symmetric, and it can be written as 1 by 2 into 0, 1, 1, 1, 0, 1 and 1, 1, 0. And the power delivered to the input of the divider is given by P in is equal to 1 by 2 into V1 squared by Z0. While the output powers are P2 is equal to P3 is equal to 1 by 4 into P1, which shows that the half of the supplied power is dissipated in the resistor. Next we will see about the Wilkinson power divider. The lossless T-junction divider suffers from the disadvantage of not being matched at all ports, and it does not have isolation between output ports. The resistive dividers can be matched at all ports, but even though it is not lossless, isolation is still not achieved. The Wilkinson power divider is such a network with the useful property of appearing lossless when the output ports are matched. That is, only the reflected power from the output ports is dissipated. It can be divided in even and odd mode analysis. For simplicity, we can normalize all impedances to the characteristics impedance Z0 and read out the circuit which we have seen already, and the voltage generators at the output ports as shown in this figure. Okay. And this network has been drawn in the form that symmetric across midplane. The 2 source resistors of normalized value 2 combine to in parallel to give a resistor of normalized value 1 representing the impedance of the matched source. That is, the quarter wave lines have a normalized characteristics impedance and the shunt resistors has a normalized value of R. And for the equal split dividers, these values are given by Z is equal to square root of 2 and R is equal to 2 as shown in this figure. We can see in this figure, right? So now if we define the 2 separate modes of excitation, that is, the even mode is defined by Vg2 is equal to Vg3 is equal to 2V0, and the odd mode is defined as where Vg2 is equal to minus Vg3 is equal to 2V0. So superposition of these modes effectively produces an excitation of Vg2 is equal to 4V0 and Vg3 is equal to 0, right? From which we can find the scattering parameters of the network, and we can now treat these 2 modes separately. For that, this is the diagram of the even mode. For even mode excitation, Vg2 is equal to Vg3 is equal to 2V0. So V2 power 0 is equal to V3 power A, and therefore so current flows through R by 2 resistors of the short circuit between the inputs of the 2 transmission lines at port 1. So we can then bisect the network with open circuits at these points to obtain the network, which we have seen in the previous diagram. And looking into port 2, we can see that the impedance Zn is equal to Z square by 2. For odd mode, Vg2 is equal to minus Vg3 is equal to 2V0. And there is a voltage and along the middle of the circuit, and we can then bisect the circuit by grounding it at 2 points on its midplane to give the network. That is, loading into port 2, we see the impedance R by 2, since the parallel connected transmission line is lambda by 4 long and shorted at port 2. Thank you.